Okay, thank you very much, Dr. Werzer, for accepting our invitation to participate in the second Immerse School. Let me introduce your webinar to the audience. So, Dr. Oliver Welzer from Joanneum Research Institute in Austria will speak about do nanogenerators or paper-based PCBs make Internet of Things more sustainable? So this is a question that I think he will try to reply during this webinar. A few words about Oliver. Sorry. Oliver is a scientist at Joanneum Research in Austria and currently working on 3D nanogenerators and PCB alternatives, employing additive approaches. Prior research topics involved structural analysis of organic semiconductors, drug molecules, as well as ionic liquids in the bulk, as well as thin films. So thank you very much for accepting our invitation. And the floor now is yours. Thank you.
Okay, thank you, Kostas. Can you see my presentation?
Yes, everything is fine. Yes.
Everything is fine. Perfect. And thank you very much for inviting me and giving the opportunity to show some of our results. And we think how we can use them for a couple of different things. And hopefully we can answer a little bit the question we had put here at the beginning. Do nanogenerators or paper-based PCBs make IoT more sustainable? So very quickly, just to give you a little bit of idea what we are doing, Joanneum Research is a RTO based in Austria. We have about 500 deploys, 7 units distributed among many places in Austria. I myself work in the subunit of materials. That's the Institute for Sensors, Photonics and Manufacturing Technologies. That is again subdivided into other units, and I'm based with Barbara Stadlober with the hybrid electronics and patterning in Weiz. It's a small town in Styria in Austria. We have about 30 group members, and we try to answer a lot of different questions. For instance, like large area technologies and patterning methods that include roll-to-roll pilot line, Weizer-Flex technology. I will introduce a little bit, as this is very interesting for sensors and nano generators. We do a lot of organic electronics, nano imprinting, laser lithography, energy harvesting, among many, many things more that we do. I myself, I'm here since 2.5 years nearly, and I'm involved in a couple of different projects. So I'm with the Emerge project, where I help some of the users with their problems. Recently, it also started the InfraChip project that is very similar to Emerge, but also offers a lot of stuff for inorganic semiconductors. Then I work a lot in the Symphony project. The Symphony project deals with nanogenerators and how we can use them in different use cases. And finally, I work in the Circle Paper project, where we try to replace standard FR4 PCBs by paper-based PCBs to get a little bit advantage of everything I will show in a minute. So IoT, many people hear about IoT, so Internet of Things. A short history, it's not that long that the World Wide Web was actually invented, so it was only in 1989, and since then a lot of things have happened. But when the people started to do things over the World Wide Web, they realized, okay, we can actually also do some manipulation over the internet. And one of the first things that was reported was here the toaster that could be turned on and off over the internet. So you could more or less start using automation via the internet. It took another couple of years, then the first webcam was introduced, so that we can also have a look at what's happening on other places in the world. And there were a lot of things introduced in between. Until then, there was not much information about Internet of Things. The information I got from this homepage here, written on here in the top right, is telling that 2008, somehow the IoT was born. And according to Cisco, it was conceived between 2008 and 2009, when the number of connected machines surpassed the number of humans on the planet. So there was a lot of things going on. The homepage might be a little bit old, but back then it had about 21 billion connection. I think we are now around 9 billion people, so it might be already from some later years. Anyway, the number of devices is increasing ever since. So the question is, how do we define actually IoT? What does it mean? And for sure, you find a lot of internet resources where you can have a look. Wikipedia is always your first choice, I guess. And it says the IoT describes devices with sensors and that are more or less connected and exchanged over a communication network or via the internet. Very similar thing you can find from other companies like Infineon, semiconductor company, also based here in Austria, one big fab in Villach. That is the Internet of Things connects physical objects with the virtual world. So everything we can somehow measure, we try to translate and use this information to do something. With the help of the technology, they collect relevant information about the location, local environment, analyze and link it. So that's what they are telling. Amazon is even going a little bit further. So again, it's a network of connected devices, and that also tries to communicate with each other. And due to the inexpensive computer chips and also sensoric and also high bandwidth in telecommunication, we have now the possibility to connect billions of devices over the internet. That starts from here, they tell like toothbrush, vacuum cleaners, cars, machines, and so on. So you can, everywhere you can put your sensors. You might also use this information for whatever purpose. The question is, why do we want to put sensors everywhere? In former days, I thought, okay, putting a sensor in your coffee machine or your toaster doesn't make sense. But actually, we can learn a lot of things from the habits of people. And found here some interesting summary of how IoT can actually help to overcome the challenges that we have in the world. So first of all is the understanding of environmental impact. So many people don't realize that they actually do have an impact on the environment. And if you are not able to somehow see what we are doing, then we have no clue how to change what we are doing. So what we want to have is we want to have real-time data, and we want to have a better understanding of the impact that we actually have. When we have IoT devices, we can also do smart energy management. So one of the most significant contribution is this, and it enables the real-time monitoring and control of energy consumption. So we only produce energy when we really need it. That's one thing. So having a smart grid, for instance, this can be strongly facilitated by IoT devices that we have in our surrounding. We can use IoT to do efficient resource management. So we have smart sensors embedded in infrastructure and manufacturing processes, and then we can directly detect resource usages, detect inefficiencies, and most importantly, can suggest improvements. So what can we do better to get things done? So this can lead to significant reduction in water consumption, material waste, or so on and so on. Precision agriculture is another topic. So if you want to put down your fertilizer in specific places, for instance, to grow more crops in this particular place, then IoT can help you quite a lot to actually achieve this kind of things. Waste management and recycling in a smart way allows now to have like smart waste bins that can tell you when they are actually full. They can tell the company to come along and pick up the garbage. This reduces the traveling times and the collection routes, reduce fuel consumption, and therefore for sure a lot of emissions. IoT can facilitate much better sorting and recycling in practice. So if we do a better sorting at the beginning, then the recycling process might be also done much better. Environmental monitoring and conservation. So we can check air quality, water pollution, wildlife habits in real time. And we can have a look if we have areas that we need to be concerned of and need some changes of our side. Another thing that's very interesting, from my opinion, is the creating eco-conscious consumers. So every time you tell the people that they actually consume too much of energy, they produce too much CO2, things like this, people will go and have a thinking. And so over the time, I think people will make much more sustainable choices, what they are actually doing. So what is needed to actually install a IoT, let's call it network, where we have everything together? So we need our devices that might be just very simple devices, as we have seen here in the as it is seen here on the left-hand side. So just cameras or all the kitchen tools you have, for instance, or you have your fan in your living room, whatever. They all might be connected directly to the Internet of Things. This can be done in different ways. I don't want to go into specifics, but all of this can also transmit some information back to the cloud. So when we do this in a more abstract way, so what do we need to actually establish this kind of work? So we need to have some energy to do actually something, and then we want to have a sensor. The sensor we want to use now for actually detect something that is of interest. Might be that someone entered the room, might be the brightness of the light on the outside to change the blinds in the house, or it might be temperature that is dropping due to the bad weather conditions. All this can be detected by the sensors. This we feed then into data processing and transmit into the cloud via different technologies. So the question is, how many devices are there in the world? At this stage, I think it's not easy to tell or give exact numbers. It's always an estimate. But as we see here, stated that there are over 15 billion connected IoT devices worldwide, according to this information. If you have seen the other page up there, it's telling something about 21 billion. So it's some kind of gap, but you get the idea. We have a lot of devices that are out there. One thing that is clear is that everyone wants to use sensors and IoT devices to do a lot of different things. And so it's estimated that from now on, it will nearly double to up to 2030. So in only 6 years' time, this number of 15 billion will increase quite drastically. Especially China, it's estimated that they already have 5 billion devices in their place. And as you know, they also put a lot of effort in to get the things done. And so they will grow definitely much, much quicker than the rest of the world. Yeah, so approximately 2 in 3 in the world use IoT. And the remote asset monitoring is the most popular use case for IoT. So this is just a general statement that IoT might be used quite drastically. For sure, there's also a business case behind. So if you think about how big is the business currently, it's estimated around 1.4 billion in 2024. And this will increase to around 2.2 billion in 2028. So it's also a huge market for everyone to enter this particular field and to provide a lot of information. So, but if you think about if you're going towards really big fabrication, we will need a lot of resources to actually get everything done. So what do we need in particular if we go into more details in the scheme I had before? So first of all, we need a good computer infrastructure. That's not the business of Joanneum Research. That's far up the queue. So it's like data centers at Amazon or Google or all other companies. They just take in most of the information and to store it and process it. So you find more or less devices like this given here by Ocean or by Nordic Semiconductors that actually allowed you to transmit the information you generated at your sensor node towards the cloud. And this is typically done in silicon, so we can do much here. One thing we might think of, where can we actually provide a little bit technological advantage to actually reduce the amount of material needed in these devices. So I will show later on that actually one way to go would be exchanging the PCB by using paper-based material. Okay, the energy needed to actually transmit some information over the internet is not as big. So we can use as little as 100 microjoule to actually feed the information we gain from our sensors into the internet. And so that's the size range we are interested in to actually generate when we're speaking about energy harvesting in a second. So in terms of sensors, what kind of sensors are we interested in? In principle, there are many, many different sensors. And here it's just a summary of just conventional sensors like proximity sensor made from inductive or capacitive technology, ultrasonic sensors, gyroscope, and so on and so on. And depending on what you want to measure, you will have different kind of sensors, that's for sure. If you look on the sensors, you see they're quite bulky, as they not only have the sensing part, but also readout electronics, things like this. So you need to also spend a lot of effort to actually produce these sensors. One way to overcome this problem is now to exchange the standard sensor technologies by printed sensors, where you actually use now additive manufacturing. I think Valerio showed interesting results, I think on Tuesday, what you can actually do with printing. And there we can deposit our sensors on substrates that are much more sustainable and might also have different advantages, like a strong flexibility indicated here by the roll-up of our sensor mat that we have. Okay, to actually get everything running, we need some energy, and like shown here on the left-hand side, for sure, we can have a big power plants, hydro power plants like here in the Alps at Kaprun in Austria that produce a lot of energy. The same you can do with wind turbines that you just put in every place where it's windy. And solar cells for sure is really, really popular. Provides a lot of energy. So the question is it always good to have this large centralized power? And actually, it's not as easy to use your sensor node with energy that's coming from very far off. So you need cabling and installation, you need maintenance, and so on and so on. So sometimes it's easier, rather than using this energy from big power plants, using batteries might help you a lot. For sure, next problem, having batteries, they have limited lifetime. At some point you need to change the battery, so the maintenance is quite complicated. If you think about IoT nodes along a train track and you want to place sensors every couple of hundred of meters, this will be quite exhausting if you need to change batteries over these far distances. So using self-sufficient energy autark systems that can help, might help you a lot in doing what you are interested in for the Internet of Things. So one thing you can use is for sure solar cells that you can simply scale in all kinds of sizes. They are quite good, have for sure there are some limitation. But over the years, or let's say 20 years, people realized that we can actually also harvest energy from much smaller energy sources. And this includes things like thermo or pyroelectric effects that we can just use to actually get energy out of the environment. And another way would be piezoelectric generators, where we squeeze our material to actually generate energy. We can use triboelectric generators, or we can even harvest the radio frequencies that are just floating around in the air close to us. So as they produce only very little amount of energy, we typically tell that these are so-called nanogenerators, and they are quite interesting in terms for remote areas or difficult accessing location to actually provide energy or to produce energy at the site where we actually need it. And as I said before, for a single transmission, a couple of hundred of microjoule might be sufficient to transmit the information already from your sensing device towards the Internet of Things. Here on the right-hand side, it's just indication. So you could use like a triboelectric sensors with power densities of up to, what do they tell here, 400 watts per square meter. So if you do a proper job on your triboelectric sensor, you might provide this amount of power, or you can use a piezoelectric as indicated down there. So nanogenerators, what kind of nanogenerators are out there? And I can tell you there are many, many different. For sure, there's some common technology behind some of them, but people are really creative in designing a lot of different things to harvest energy from all kinds of sources. So a nanogenerator is in principle a compact device that converts mechanical or thermal energy into electricity. And this is serving as an energy harvesting solution for small, typically wireless autonomous devices. So that's what nanogenerators are thought of to be used. If you want to use nanogenerators to provide energy for the entire city, this will not work. There's not sufficient energy around, so this is not the best technology. But thinking for small wireless autonomous devices, nanogenerators are a perfect choice. The nanogenerators typically tap into ambient energy sources like solar, wind, thermal, or kinetic energy that is always in the background. So if I go into the outside, it's warm, I have a lot of thermal energy. If the sun is shining, I have a lot of photons that I can use for my generation of energy, and so on and so on. In urban areas, we even might, as I mentioned before, like using the power lines, they always transmit electromagnetic radiation, and this is typically also sufficient to do harvesting on a very small scale. So if you have a device that is close to a power line, this might be run just by using a nanogenerator. When we had tried to publish some of our results, we came to the discussion with the reviewer that nanogenerators might have different meaning to different people. And so here I want to say that nanogenerators for me typically relates to the amount of energy or the power that we can provide. So we having typically in the range of nanojoule or nanowatts that we have, and this we can provide on a regular basis. For some people on the other side, they refer nanogenerators for the dimension, so having a very small devices in the nanometer regime, or the effect acting on these small scales, they tell that it's nanogenerators. So I think I leave it up to you to decide how to use this in the proper way. I think UPAC hasn't decided yet what's the best alternative, best definition yet. But anyway, so how can you use nanogenerators? So if here it's just two sketches I found from publication, they're summarizing different effects that we have, like nanogenerators from triboelectric, pyroelectric, or piezoelectric effects, so all possible. And you can run all kinds of sensors as indicated here on the right-hand side, where you run like infrared sensor, artificial skins, and things like this. When you think about the energy source, where can you take it? One thing that's very popular is for sure you're using wind energy, for instance. It's very popular to be harvested. You can use even the wave movement of the water waves in the ocean, as you have a lot of mechanical energy there. You can also try to harvest this kind of energy, and so on and so on. And the bottom line here, it's indicated that the amount of energy needed for some application is so small that you can even harvest this in living organisms. So some of the researchers put the harvesting devices like on the heart to actually use the heartbeat to generate energy. So the mechanical movement or the mechanical energy of the heart muscle is now transferred into electrical energy that we can use for some application. You can use like things like bladder pressure to actually inflate or deflate the some of the devices, and use this kind of mechanical energy. So the ideas are quite widespread, I would say. Not all of them, I think they are ethical correct, but I think it only shows that there are some possibilities that we even for biological environments, we can use nanogenerators to get energy out of a system. Okay, speaking of different devices, I will just show a couple of different devices that you can use for your IoT devices. One thing that's very popular is so-called triboelectric nanogenerators. If you so triboelectric effect might be quite commonly known for everyone. So if you have very dry hair, for instance, you rub your hair with some plastic, typically you start charging your hair and all the hair spreads away. And this is due to charging of the individual hair by charged particles. And from this, you can more or less get the potential to spread your hair. If you use the same effect, you can more or less now take the charges and transfer it to different surfaces. This is indicated here on the right-hand side. So you take like an aluminum electrode and you push it towards a Teflon block, so a block made from PTFE. And since the PTFE is very affine to electrons, they suck a lot of electrons from the aluminum. And so we can transfer some of the charges from the aluminum towards the PTFE. When we separate then these two surfaces, what we produce more or less is a capacitor. And this capacitor we can now use to, when we're moving up and down, we can use to generate energy. So that's one way of doing the triboelectric nanogenerator. In different setups, you can not only use a single electrode like indicated here, but you can also use electrodes on the top with a second dielectric layer in between. You can manipulate the amount of triboelectric charges generated. But it depends a little bit on your environment, how you want to set up everything. So the triboelectric nanogenerators, or TENG in short, can reach nowadays up to 500 kilowatts per cubic meter if you use a density for the for bulk density, or up to 300 watts per square meter if you just think about thin films in the surrounding. Another effect that you can use for generating energy is the so-called piezoelectric effect. So already in 1818, the physicists Jacques and Pierre Curie discovered that some materials, when you push on them, produce electric charges that you can then measure on the outside. So a piezoelectric material, just in short, I don't want to go here into details, know about the knowledge about all people in the audience, but just quickly, when we squeeze such a material, what we do is pretty much we have atoms in our solid. We now shifting the atoms in the unit or in the bulk in that way that all the charges are somehow shifting. And if the shifting is not done in a symmetric way, we will end up with a slight with a dipole. That means that some of the charge is not counteracted by another charge. And this we can now use to actually generate energy in all kinds of ways. What kind of materials can we use for this? There are natural materials, you just find it in nature and you do your experiments, you will be able to see this effect. Nowadays, a lot of effort is put into ceramics. Ceramics with complicated compositions of materials also allow you to make high power piezoelectric materials. But the big disadvantage is you need a lot of energy for their production, and they are quite brittle in terms of when you want to touch them. So in recent years, a lot of effort was also driven towards polymer films. So you can use polymers like PVDF, chitosan, polylactic acid, and things like this to achieve similar things. In terms of performance, the performance is always much better in a ceramic. But having these polymeric films, they allow you to do a lot of interesting things that you cannot do with ceramics. Okay, so just quickly, how does a PVDF TRFE piezoelectric material work? So you have your chemical groups like shown here on the downside. So we have the polyvinylidene fluoride side here on the left-hand side. And when you deposit this material, you typically end up in a specific polymorphic form. So it is the alpha form and the beta form. And it was shown that you actually need the beta form to have a good piezoelectric behavior. Then people realized, okay, we can co-polymerize this polymer on the left-hand side together with a 3-fluorine ethylene group. And this actually provides the possibility for the original block to crystallize more or less in the beta phase most of the times, and so you don't need too much effort to actually get this beta phase done. When you deposit this material, you need to do a little bit of rearrangement of the dipoles. This is done by electrical bowling. So you apply high electrical potential, so it's about 50 volts per micrometer that you need to apply to actually align all the dipoles in one direction. And with this, you can establish a very good piezoelectric device that you can use on the one hand now for generating energy like a nanogenerator, or you can use it as a sensor. The technology we developed here in the house is called the BitFlex technology, and you can now use printing technology to actually prepare this kind of devices. How is this done? Quite quickly. So we have a substrate that might be made from plastic, paper, glass, whatever you think of. You put down the first electrode, you put up the second, the layer of the piezoelectric polymer. So in this case, it's PVDF TRFE. That comes out from a solvent, and after solvent removal, you put down the second electrode, put down the electrodes, and you are ready to go for the bowling process. So after the bowling, then we can use this device to get things done. So what can we do with this kind of device then? So in the project Symphony, we developed a couple of different things. So this I want to show here. The first one is a nanogenerator for flow application. So I think best to see what's going on is here on the left-hand side, when there's this cyan greenish cantilever system. So it's written on piezoelectric layer that is sitting on a cantilever that is made from a plastic, so in this case PET, and we have a spacer structure. When we now start bending our piezoelectric device, we will generate energy. The bending is shown by simulation that it's much more effective to provide us energy compared to when we just have a normal load. And having this kind of device, we can now produce a decent amount that we can actually use for doing something. This is indicated here on the right-hand side. So when we make a small assembling, indicated here by this bottom space structure, the peng and the top space structure, we can actually squeeze many of these cantilevers at the same time. And when we do this for 16, as indicated here on the right-hand side, that each time we jump on our device, we push it, we squeeze all of the 16 cantilevers, we're producing about 4.4 microjoule for the first step, 6 for the second one, and so on and so on. So the increase here is due to the change of the loading capacity of the capacitor, so the impedance matching is changing on the different number of steps. But as you can see, we've been producing 4 to 6 microjoules. I said before, we need 100, 200 microjoule for making an IoT device suitable out of this kind of structure. So we went in and improved this even further. So we installed now, rather than 16 cantilevers, now we installed about 200 cantilevers. And when we now put this into a circuitry that's indicated here on the right-hand side. So we have a peng, the piezoelectric nanogenerator, that provides us electricity. This needs to be rectified as on the load and deloading of the device. We will have the current flow in opposite directions. So we need a rectifier to actually get the charge rectified. You can store it in a standard cap. We have a comparator that just checks for the voltage on the capacitor, and when we're reaching the level that is needed for the transmission device here in Ocean device, then it will just switch through and we can transmit the information. So in this particular case, we need about 150 microjoule per step to have a transmission, and then this device transmits a ID beacon over the ether, and we have a receiving unit on the other side of the room, and we can just do something with it. One thing you can do, for instance, like switch on a lamp, or you can also hook it up to your smart home. So how does it look in real life? I'll show it here. So my colleague is walking over this ground plate. So the ground plate hosts now the different cantilevers. As she goes on, you see in the when she puts on the second foot, the lamp on the backside starts lighting up. And this is actually due to the fact that we now producing energy, we're storing the energy, then using this energy then to transmit some information, and we're telling just the lamp to switch on and off by jumping up and down. For sure, you can use different information. So like in a security case, you can open a door, close doors, things like this. This is just an illustration how this could work. Okay, having this technology, we're not only limited to putting this in the flow application, we can also do other things. One very important thing is so-called condition monitoring. Condition monitoring is now a technology that tries to figure out malfunction of devices before they're actually happening. And so by measuring a lot of parameters, typically you can tell that the machine is running smoothly or there's something going wrong. One very interesting work was done by our colleague. So he wanted to see if he can harvest enough vibration energy to actually run a condition monitoring system on a rotary pump. So this rotary pump is just from our glove box, and typically it's shaking quite a lot. It makes a lot of noise, so we know there's a lot of vibration around. When you mount then here on this green box, it's indicated the so-called energy harvesting system. You can actually harvest a lot of energy. How is it working? We typically have a cantilever on the inside, and this cantilever is allowed to move up and down. If we move this at resonance with the surrounding pump, we will have a huge amplitude. When the amplitude is at this maximum, we typically produce a lot of energy. When we're using this energy and putting this in the rectifier and in energy storage, we can do something with this. And this is indicated then in the next block that's indicated by this blue box. In this, we have a sensor that might be a temperature sensor or accelerometer. So the accelerometer might allow to determine if the vibrations are still in a smooth way or they are somehow deviating from what we are expecting. If they start to deviate from the expected one, we typically tell, okay, let's go and have a maintenance on the pump. The information in this particular case is transmitted via Bluetooth to a receiving station that is somewhere a little bit off this vacuum pump. So how much energy can we generate with such a scenario? So before we had the single event at 150 microjoule. As we're using here a much more demanding sensors and transmission, we need much more energy. But over time, we can actually generate a lot of energy. So due to the fact that we're shaking all the time, we can produce here in the green scenario, for instance, we can produce 45 millijoules within 22 hours. So now you're telling 22 hours, that's quite a long time. But in terms of machine conditioning, that's sufficiently. So you don't want to measure it every second. That's not of interest. Typically, you measure it a couple of times a day, and that's sufficient to know if your machine is malfunctioning. And having this kind of device, you have now a self-sustained possibility where you just mount it on the surface and you can tell about the conditioning of the machine. You can use this also on much bigger generators or moving parts. And it can also facilitate this particular type of harvesting. Okay. Third thing that we did in the Symphony project is indicated here, that we actually, together with the project partner Tubolito, a manufacturer of tubings for bicycle tires, they want to have information about the pressure inside the tube when you are riding your bike. And the question is how you can do this. There are a couple of different ways, but one idea was to actually use energy harvesting on the inside of the tubing to actually get all this information out from within the tube. Therefore, we placed some sensors on the inside. It's a little bit hard to see in this particular image. Then we placed the tubing inside the tire, and then we mounted it just on the bicycle. And when we do so, we can generate as much energy to transmit every 60-second information about, in this particular case, the pressure and the temperature on the inside of the tube. When you run it, for sure you need to run it for a very long time. So you do stress testing. So this ran, I think, for 5,000 kilometers, quite good. And we can demonstrate that this is a really good product. The good work was also appreciated at the LOPEC as a best public funded demonstrator in this year's LOPEC competition. So if you want to have more information, you can find it on the Symphony homepage. Okay, having Pizoflex materials, we can also use it as a sensor. So here just quickly, then we don't use the energy that we are producing, but we can use the information that the sensors are providing. Just start all the videos at the same time, so we can determine the temperature changes. We can use it as a touch sensor, bending sensor, or even we can determine vibrations or acoustic sensors. All is possible with this kind of device. So just thinking, so we having another 6 minutes, or how long do you want me to speak? Just
I think we have time, yes.
Okay. So when we have now these devices, what we realize is for sure increasing the number quite drastically, as I introduced before. We also need to think of how to produce everything. So semiconductor facilities are quite at their limits, so are the PCB manufacturer and so on and so on. And the things also happening is we need a lot of resources. So the question is how to improve. One way to go would be using additive manufacturing. That is typically less resource demanding in terms of material, energy, and so on. And we could use sustainable materials wherever possible. So exchange the glass fiber mats and epoxy resin by paper. This might help quite a lot. One thing that we also need to keep in mind is at some point we need to, at the end of life, we need to think of what we are doing with the devices. So we need to have an idea about the reuse, upcycle, recycling strategies, and so on and so on. So that's one thing we now working on in the Circle Paper project, where we now think of how to do. If you think about the PCB in general, they're very sophisticated, highly technology or highly developed technological parts. Without them, you cannot run anything in your electronics. So they are really engineered to nearly perfection, I would say. The big problem is you need to have a subtractive manufacturing in general. You have a low amount of bio-based materials as well as recycled materials. So you need a lot of resources, and the end of life of this kind of device is really bad. So we still don't know how to deal with all the e-waste that we are producing from this. So employing other approaches like using now paper instead of standard PCBs. So we're taking here the green part, that is the so-called FR4 for fire retardant 4 level PCB. We could just replace this by a paper sheet, and then we print everything on or deposit everything on paper by printing lines using like screen printing or inkjet printing, and then gluing all the components. So having a look on this side, we see that we have a fully functional sound card in this case. So you can press a button, it will play some music, or you can record something. And the very same you can realize using here the paper. So by just thinking about all the different points and bits, so new circuit design, material development, process development, and assembling strategies, we can actually replace quite easily the FR4 by paper, but only in certain range. So the paper performance is good, but compared to FR4, and especially in high power application or high frequency application, we will have some troubles. But for low power application and low speed demands, paper is really, really good. A paper by Liu et al. Already showed in 2014 that actually you can replace the FR4 by paper. So it's they're demonstrating even wire formation and fully functional devices. So pretty much what we rebuilt in our case. And what they did is they did some LCA analysis. So LCA lifecycle analysis, they put all the information in they got from the manufacturing of the standard PCB here on the right-hand side, and on the left-hand side, they had the paper-based PCB. So you put in the silver flakes, for instance, like as raw material, paper, resin, and so on, and on all the different process steps. This they did for both and had to look which one is performing better. One thing for sure that's always a little bit complicated in this kind of analysis is if you don't do everything on your own, you will not have all the information. So it's sometimes a little bit guessing, but I think the research is going in a good way that we actually gain more and more access to all these important bits and that we can stick them together. So two outcomes that I quickly want to show here of this is when they had to look on the emissions in the production, so like carbon dioxide or carbon monoxide, you see that here PCB stands for printed PCB, O PCB stands for organic PCB, like for the organic resin they're using for producing. And you see that the standard FR4 O PCB always emits much, much more gases compared to the printed PCB. So by just using paper process like indicated there, you already improve quite a lot. Very similar thing is outcoming when you have the different indicators, having look into, for instance, the, I don't know what we should look at, acidification potential, the AB, you see that the epoxy-based PCB again has much more potential to harm the environment compared to our paper-based PCB. So by using this strategy, I think we are on a very good track to actually help providing enough tools for IoT manufacturing for the near future that is also not destroying the environment more and more. When we think about how we can fit this in the in the sustainability ranking in this 9R ranking, we see that we can refuse, rethink, and reduce a lot using this approach. So refuse, we can take away a lot of materials that are harmful to the environment, and we can think of new approaches to actually manufacture in a different way. We can reuse, refurbish, remanufacture, so that's working quite well. One problem with paper PCBs is the repairing of paper PCBs is not as easy as we're using conductive adhesive most often. If something goes wrong, exchanging parts is quite tricky. So that's also one thing that we need to come up in the future, how to deal with this. Recycling of many components in the additive manufacturing is possible. So we can, especially if you don't use too many of the coatings, then the paper can be recycled quite easily. So there's be the silver lines and so on. At the very end, if we cannot recycle, we might even burn the entire PCB and recover most of the components from their side. As we're using biosources as a starting point with wood, the CO2 balance should be very in a reasonable range, let's say. So to conclude my talk, we typically use nanogenerators for remote and inaccessible areas. So if you have a machine and you don't want to climb up there all the time, you can mount a nanogenerator, for instance, and the power should be just sufficient to transport the information you want to have. So it's no point in producing a lot of overhead energy if the only thing you're interested in is a small temperature information every 5 hours, for instance. So we can actually tune this and use the proper nanogenerator. We should also exchange problematic substances like PVDF. It's a wonderful material in terms of application. As you have seen, we have a lot of fluorine in this particular case. And as you might be aware, in the European Union, we shouldn't use too much fluorine hosting polymers anymore. And therefore, we also need to look for alternatives. So, for instance, like polyl lactic acid might be an alternative in the future. In terms of PCB, we need a lot of effort to actually get something done, but we can use additive manufacturing. And by using this additive manufacturing, we can also think about scalable processes like roll-to-roll printing to make not only like 2 sheets in an hour, but we can print like hundreds of meters per hour with a big roll-to-roll machine. The LCA indicates that this paper approach is much better in terms of sustainability, and the circularity of the paper should be also much better compared to standard BCP. So to this, I come to an end. I want to thank you for your attention. And if you want to contact me, here's just some information how to find me. So,
thank you very much, Dr. Werzer,
yep.
for this very nice talk, very nice results. Let me check the chat for questions. Tammy is asking that as you demonstrated nanogenerators using ferroelectric polymers, how do you think the use of more sustainable materials will affect its overall performance? And what are the challenges with achieving this?
Yeah, so using ferroelectric polymers, that they work really, really well, and so especially the synthetic one that we tested so far, they're working. Having more sustainable materials, we have some interesting results, but you're right, the performance is much, much lower compared to what we have. There might be a lot of reasons for this. So the impurities of the material might be quite high. The choice of the polymeric form. So if you need to pre-process, for instance, to achieve a better arrangement of the different components, we need to check. So it's not like we just take out the one polymer, stick in the other polymer, and using more or less the same process. We still struggling to find the proper process to have a good performance on the PLA and the chitosan. So we will see. But there are also other molecules, for instance, like glycine, a very small molecule. It's promising to have really high ferroelectric performance. But again, we haven't achieved now a good result so far.
Okay, thank you very much. Any other question? You can speak directly, or you can write down the question to the chat. Meantime, I have a question about these nanogenerators. Of course, they can provide very limited amount of power. So the loads that we can provide power is this should be, low power applications, I understand. Yeah. How you can overcome this? Can you connect in series, for example, many nanogenerators and scale up the voltage?
So there are a couple of ways how you can deal. The one thing is you just increase the size of everything. So rather than using a small square centimeter, you just scale it up to a couple of square meters. You can do a stacking, and so you can somehow try to squeeze much more material in smaller areas. The second thing is you're looking for a proper excitation. So having the floor application where you have a human walking over, you only press it once every now and then. If you have a shaking device like the electrical motor on the bump I showed, it's moving all the time. So rather than having a frequency of only, let's say, 1 Hertz for the single excitation on the walking, in the electrical motor, you might have a couple of hundreds of hertz. So you increase the power output also by this amount, by just using much larger excitation. So triboelectric nanogenerators, many people also tend to like using wind for harvesting. And if you have a fluttering device that's like a flag in the wind, you can generate really high power. The problem sometimes is just to find the material that can withstand this very high frequency over a long period of time. So it's really interesting to show on a small scale, but if you think about the power plant that is running 24/7, very high loads, many of the devices I showed you today, they're still a little bit limited in terms of longevity. So yes, there are approaches to upscale, but it's not as easy.
Yes, I think for the application, for example, in the pump or the plant that you said before, you have more or less continuous operations, or continuous harvesting. But for other applications, as you said, most of the time you are at the idle state, so you are not harvesting any energy. So in this case, you need any external battery, supercapacitor, or some other source, or another complementary energy harvesting, for example, combine solar energy with piezoelectric, just to have all the time continuous power.
No, definitely. So we in one partner in our Symphony project is a company that's producing condition monitoring system for wind turbine blades. And so far what they have is the situation that they're using solar cells to charge up their device. And they're quite happy with this. But now they are able to increase their market towards Scandinavia. And during winter time, you don't have much solar power. So therefore, they're looking for something else, and having now a nanogenerator like we develop might now allow them to also charge the devices during winter times when they only have limited hours of light. And so combining different devices, that's a very good option. And if you're producing an overhead of energy, you might also store it. So in the Symphony project, we also tried different storage alternatives like capacitors and batteries, things like this. That's also an option. So if you need this overhead, then you can also install it with storage devices.
Okay, thank you. Any question from the audience? Meantime, I also would like to ask about the cost, the actual cost. For example, this smart floor application that you showed us.
Mm-hmm.
What is the cost to update your floor, your house, with this nanogenerator?
So that's a little bit hard to tell at this stage because we are at a very small production scale. So I think we still at a couple of euros for a watt. So for an entire house, it mightn't be not as cheap at this stage. I think when you are able to upscale the production, so you have a printing facility that allows you to print big quantities, you might go down with the price that it's really reasonable to be used by everyone.
Okay, I think I have seen similar applications in national roads. For example, you have continuous, let's say, motion from big vehicles, so you can harvest enough energy for a long time. So, okay. Any question from the audience? You want to comment? Okay. Otherwise, I would like to thank you, Dr. Welzer,
You're welcome
for your participation in our school. Thank you very much.
You're welcome. Bye-bye.
Bye-bye. So now we will move to the final speaker of the school. I'm very happy to have together Professor Aldo Di Carlo from CNR in Italy. So Professor Di Carlo, we have 2-3 minutes more to follow the program. So maybe you can share your screen to check everything that your slides are.
Exactly.
Great.
Let me try to share it. Okay. I share the PowerPoint presentation. Yes. I hope you can see.
Great. Yes, it's full screen. Everything's fine. Yes.
Okay, good. That's really great. Okay.
We started the school with Professor Ferrari and we close with Professor Di Carlo. So we are very happy.
So the same. We speak about the same topic now.
No.
No, probably not.
All of
okay.
Graphene flagship webinars.
Exactly. Yes, indeed. It was okay. So let me know when I can start.
Yes, in 2 minutes I will make an introduction.
Okay, that's good.
Just to wait because some applicants are joining only specific webinars and it's better to wait 2 minutes. And also, this morning also we have Morten Madsen from Denmark about oxides and tandems, OPV tandems. He presented your joint activities in
project. Yeah, exactly.
Solar.
Yeah, I've seen it, and so I try to speak about some other stuff. I mean, and will complement what Morten was saying this morning.
Great. So we have 45 minutes, and then let's say 10 minutes for questions.
Okay, that's good.
Great. So let me briefly introduce the speaker and the webinar. So we're extremely happy that we have together Professor Aldo Di Carlo from University of Vegatta and CNR in Italy. The webinar will be about solar modules towards sustainability. A few words about the speaker. Professor Di Carlo graduated in physics at the University of Rome La Sapienza and obtained his PhD from the physics department of the Technical University of Munich in Germany. In 1996, he became research assistant in the Department of Electronic Engineering of the Tor Vergata University. And in December 2012, became full professor in the same department. Since 2019, he is a director of the Institute for Structure of Matter of the National Research Council in Italy, CNR. And very briefly, his research focuses on the study and fabrication of electronic and optoelectronic devices, their analysis, and their optimization. He has published many publications and many research projects funded. Since between 2007 and 2019, he founded and was director of the Center for Hybrid and Organic Solar Cells, CHOS lab, which involves more than 30 researchers. And CHOS lab has generated 5 spin-off companies and a public-private consortium for industrialization of dye-sensitized solar cells. So, Professor Di Carlo, thank you very much for your participation in our school, and the floor is yours. Thank you.
Thanks a lot, Kostas. It's really a pleasure to participate to the school. This morning we were in a PhD exam, and so it's very nice that the schools we do for PhD and postdoc then will bring people to a very high maturity level in science. So our main goal is to promote science and to keep science leading also some of choices that we are doing at the global level. One of the global problems is the global warming, and so we need to keep our life and our world sustainable, even though recently it's not getting the most important topic, but it is indeed. And for this reason, I'm speaking about photovoltaics energy, and then the way this could make our world sustainable. Technology sometimes is not sustainable by itself, so we need also to dig into different technology, to find the one which is more sustainable. But for sure, what I will discuss about will be photovoltaics. So it's a green way, is a renewable way to generate electricity. We are looking always to have good students around the world, I mean, for PhD and postdoc. So if you have idea to do active research activity on new generation photovoltaics, just write me and then we can have a discussion. The direct conversion of electricity of sun energy into electricity is achieved with usually with a photovoltaic cell. The 95% of the market of photovoltaic cell is based on silicon. However, recently, actually in the last 15 years, new technology are becoming available, sometimes more in the research lab than on the market. But as I will show you in a moment, this is becoming more and more marketable technology. I'm referring to this new generation photovoltaics and to refer to the development, to present development of new generation photovoltaics. I'm like to show this plot, which is quite typical in the photovoltaic community. On the axis, y-axis, we have the efficiency of the photovoltaic cell as measured in the lab by a certified entity. And on the x-axis, we have the time of development. I show here in green the top record for silicon photovoltaics, which is nowadays around 26.8. And let me show the new generation photovoltaics. The new generation photovoltaics are the second generation, which is very well assessed thin film technology. Is not really the new generation, but I mean, it's something different compared to the silicon. For example, amorphous silicon, which is not too much used nowadays, but the other two, CIGS and cadmium telluride thin film photovoltaics are indeed available on the market. And for example, this is cadmium telluride module, which is quite black, even quite nice, produced by First Solar in USA. What we call emerging photovoltaics or new generation or third generation photovoltaics is this one, is this green shadow area, which is the domain for hybrid organic, inorganic, or nano photovoltaics. And let me just show you the three main categories here. So we have the dye solar cell that was probably one of the first member for this third generation. They developed fast at the very beginning, but then they had a sort of plateau, and nowadays the efficiency, top efficiency is 13%. Then we have the organic solar cell. Probably we have seen this morning with Morten Madsen. Organic solar cell that have they were also in a plateau state between 2010 and 2017, but recently, thanks to the non-fullerene acceptor, they increase efficiency, and the last record was around more than 19%. The last member of this category, last because was one of the last introduced, but is one of the most efficient, is the perovskite solar cell. As you can see, even though perovskite solar cell was invented in almost the first report was 2009, but only in 2012-13, people around the world realized that this was a new technology for photovoltaics. And then from 2012, with a steady pace, the efficiency was increasing up to the one we have now is 26.1. As you can see, the efficiency are pushing up and up, and they are reaching very much the efficiency of the silicon photovoltaics. But why this technology, this new generation technology, third generation technology, are important? Okay, first of all, because they are based on a new concept. The new concept is the following. So the conventional photovoltaic solar cell is based by a junction, the PN junction. So you have a semiconductor, you dope the semiconductor in a different way. You have this kind of band diagram, the conduction band, the valence band, and the energy gap. Light is impinging on the solar cell. It creates an electron anode. Due to the junction field, this charge is separated. So many of the photovoltaic cells are indeed, the silicon photovoltaic cells are based on this kind of concept of PN junction. However, it's not really needed to have a PN junction to generate electricity. And this was indeed one of the main topics for the third generation photovoltaics. So the third generation photovoltaics is based on this different concept. So you have three different materials, and you have this kind of staggered alignments of the bands. So you have an absorber, so the material that absorbs the light. You have the conduction band and the valence band of this absorber, and this is the colored is the gap. On the left, you have a material that has a conduction band much higher than the conduction band of the absorber, and the valence band which is slightly higher than the valence band of the absorber. On the right, you have the opposite. You have a valence band much deeper compared to the valence band of the absorber, and a conduction band which is just below the conduction band of the absorber. So what's happening in this kind of alignment? When the light is absorbed by the absorber, you form electron anode. Electron cannot move in this direction because you see there is the band gap of this transporting material, which we call all transporting material. So the electron is reflected at this interface and can move only on the right. On the opposite, hole cannot move in this direction because there is the gap of the material, and then can only be transferred to the all transporting material. So we call this material all transporting material, we call this electron transporting material, and then you can see without a junction field, just using the heterojunction between these three different materials, we can create an electricity, a carrier flowing out of the solar cell. This technology is the one used for the third generation, but nowadays is also used for, let's say, the new generation of silicon photovoltaic, like silicon heterojunction. Silicon heterojunction exploit more or less this kind of concept of interface transfer. Okay, this is one of the important topics. So the third generation photovoltaics use a different concept to extract the charge. Another point which I like a lot as well is the following. So all the material used for the third generation photovoltaics, like perovskite precursor, organic photovoltaic materials, or dyes for dye solar cell, they are more or less inks, so they are in solution. So you can use solution processes to create this solar cell. And so this is very important because you can use printing technology like inkjet printing, slot die, or coating, like gravure coating, gravure printing, offset lithography, pad printing. So even very strange printing technology to fabricate your solar cell. So you don't need a very complex equipment like the one industry is using to create silicon solar cell, but you need just a printing, like inkjet printing, for example, or a spin coating, which is even more simple than an inkjet to create your solar cell. This is important because, of course, the equipment you need are simple, and you can have this for a lower cost. And this is also, the cost is very important because, I mean, with simple equipment, you can create the solar cell wherever you are in the world. It's not needed you are in a very rich laboratory to create solar cell. In every laboratory in the world, you can create this third generation solar cell, so you can contribute to the development of the science. So everyone in the world, wherever they are, if they are in a rich country or more poor country, they can contribute to the development of the solar cell. For this reason, the third generation photovoltaics was boosting a lot because everyone in every single laboratory around the world was able to create solar cells. Then you can ask, is this the way also to making industry out of this printing technology? Maybe not. Maybe for industry you need physical deposition. I will discuss this at the end of the talk. But this could be one way to go. I will start with one of the first member of this photovoltaic technology, which is the dye solar cell. The dye solar cell is very inspired by nature, so it's very sustainable because it's biomimetic. So in fact, I mean, if you take a chloroplast where the photosynthesis occurs, and you zoom in, you see that at the very end, the molecule which absorbs the light is a sort of porphyrin. It's a metal porphyrin ring. And this acts as an antenna and then absorb the light and then transfer the excitation, the charge to this other chain. And then you can create some chemical reaction. Then you store the energy in a chemical molecule. Of course, I mean, if you want to transfer this charge out of the circuit, you need to use a slightly different concept. And this slight different concept was introduced by Michael Gretzel and Brian O'Regan back to the 90s, at the very beginning of end of 80s, beginning of 90s. And they proposed the structure which is now called dye-sensitized solar cell or Gretzel cell. So the structure is very simple. Let me explain you. So you have a photoanode, so a glass where you have a transparent conductor to get the charge out. You have a sponge or nanoparticle of titania. So the size of this nanoparticle is something like 10 nanometers. And then there is a molecule which is attached via carboxylic group, so in a very chemical way. So you attach this molecule on the surface of the titanium. Since this is a nanoparticle, the titanium is nanoparticle, the equivalent surface is very, very large. Okay, so the equivalent surface are square meter per centimeter, so it's really, really large. And then you have this coating, conformal coating of these nanomolecules around this nanoparticle. Then the cell is finalized by using an electrolyte where the charge or everything is contained, and then a counter electron with an electron contact, transparent electron contact. So light is impinging on the cell. The molecule is absorbing the light. The negative charge is transferred via titania to the photoanode, and the positive charge is transferred via redox reaction in the electrolyte. It is at the very end an electrolytic cell. So, but then let's put in a simple way, the positive charge is transferred back to the counter electron. And so, yeah, in this way, you can generate electricity, and then you can use this as a real photovoltaic cell. So as you see, is a very, very simple, and then you can use, you can tune the molecule, you can tune the thickness of titanium, you can change the electrolyte, so you can change all these parameters to tune the property of the cell for several applications. I will show you some applications which are really related to transparency, see-through photovoltaic, like similar to what this morning Morten Madsen was telling to you. So this is a plot. You have seen this is an important plot also with the Morten talk. You have a transparency and efficiency of the solar cell. As you can see here, you can change the color of the cell by changing the dye. You can change the transparency of the cell by changing the thickness of the titanium. So you can do a lot of changing. And if you see here, these are the results of transparency and efficiency of the cell by varying dye and the thickness of the titanium. You see there are dye which are, for example, this orange dye is more transparent for a given efficiency, and there are other dye like red dye here, which is less efficient, which is less transparent for a given efficiency. Then the last development I would like to show you was a project, European project by Fred Savage that recently won also an ERC project. The results is something like that, this point here. So they were able to develop a molecule which absorbs only in the infrared. So the cell is very, very transparent, more than 70% transparency, and the efficiency is around 3%. So, of course, if you absorb only in the infrared, the transparency of the cell increase, but also you reduce a bit the efficiency. Making it sustainable, is it possible indeed to use also vegetable dyes to create this solar cell? This is a review we wrote several years ago with Pino Calogero, and which is an expert of vegetable dyes. So you can use several fruits of vegetables to create the dyes that are used for the dye solar cell. For example, you can add Sicilian red orange, grapes, pomegranate, anchovy, and other materials, other vegetables to to create the dye. And you see also the color of the dye, it's very dependent on the molecule which is inside the fruit or the vegetable. So this is a very green way to create dye solar cell. Let me show you a facility for fabrication of dye solar cell. It's a facility that nowadays is at the CNR. And then you can see, so this is, for example, is the screen printer where we print the titania paste, and then the glass with the titania paste, with the nanoparticle of titania, are moved into an oven for the sintering of the titania. Of course, oven impacts. So this is the final step of the assembling of the panels and the modules. And then this is a robot that moves, that takes these panels and assemble these. Actually, these are submodules that assemble these submodules together for making the final panel. I will show you the robot now that puts this submodule in a holder, okay, here, and then it takes another one and moves the submodule to an exact position close to the previous one, and then you can create one submodule after one submodule to create the final panel. So this is the final panel. As you can see, there are 7 submodules glued together to create this semi-transparent red color panel. And you see, changing the molecule, you can change the color from green to red via yellow and orange and bronze. And the efficiency, unfortunately, is a very nice technology. It's very sustainable, but the efficiency was never on large area, never larger than 5–6%. So it's good, but not too good. Then you can use this material, for example, for in a greenhouse. So you use these semi-transparent panels as a cover of the greenhouse. The color, the red color, is the color that that plants use to grow, and all the other colors are absorbed, so are generating electricity. So you can at the same time protect the plants, generate electricity, and also transmit the light, only the light that is needed to the plant to grow. So this has been realized, and then we didn't observe any difference between plants with and without the photovoltaic, semi-transparent photovoltaic cover. Another application is the following. So this is a sort of tandem where in the front we add dye solar cell, and on the back we add an algae bioreactor. So we generate algae and we create the biomass. And I can show you here that the biomass production as a function of the light transmitted is independent from the fact that you have a semi-transparent dye solar cell on the front of the bioreactor. You see, with and without the dye solar cell, the production of the biomass as a function of transmitted light is exactly the same. For this reason, you see the total energy conversion, which is the sum of the two, because you can generate electricity by burning the biomass. So you see the total energy conversion is without dye solar cell is, you see, in the best condition was 4.5. With adding the dye solar cell, we can also generate electricity from the front dye solar cell, and then the efficiency increased more than 6%. Now you can also optimize the biomass. You can choose a beta algae that absorbs beta in the red part of the spectrum, so the part which is transmitted by the dye solar cell. And then you can see the last results was for a few years ago. You see that it's possible to push the efficiency of the tandem more than 10% by using this new algae, which is Anthrospira maxima, instead of Schendermus obliquus. Now let me move rapidly to the perovskite solar cell, from the disolar cell to the perovskite solar cell. And the main contribution was by David Mitzi. He was working on this allied perovskite. He was working allied perovskite for electronic device, being a ferroelectric material. David Mitzi, working at IBM, was considering this material for memories and for many other devices, but he didn't consider to use for solar cell. This idea to use the allied perovskite in the disolar cell structure came from Akira Kojima and Tsumoto Miyasaka back in 2009. So Akira Kojima, that was working in on electronic device by using allied perovskite, when moved to Miyasaka, that was a very good expert on disolar cell, he was proposing to use this material for as a dye for disolar cell. So they did this experiment. The result of efficiency was quite low, was 4%, so quite negligible. So they published in a good journal, but of course was more a scientific curiosity than a real impacting results on the photovoltaic community. But later on, the big groups of Kanazidis, Snate, and Gretzel realized that this was not only a scientific curiosity, but a breakthrough. And from 2012, they realized the solid-state version of disolar cell, and then the groups realized that this was a new technology. It was nothing to do with disolar cell. And this was the beginning of the perovskite solar history. And from 2012, the world was changing by the introduction. The world of photovoltaics was changing by the introduction of the perovskite. So let me show you what is the perovskite and what is good for. So the perovskite is just a generic name of a crystal structure. We are focusing on allied perovskite. So this is the conventional structure of the perovskite. We are focusing on allied perovskite, where these red atoms are allied atoms, iodine, bromine, chloride, and they are not oxygen, which is common for oxygen-based perovskite, which is very common on the Earth crust. You see there is a central cation, which could be an organic or organic cation. And then there is a metal, which usually is lead or tin. Of course, lead, we open an issue on sustainability, which is very debated in the perovskite community. This material with allied methylammonium lead iodide, for example, one of the material in this class, is very good, and many other are also very good, because they have a direct band gap, so a very strong optical property. The gap is quite ideal for photovoltaic absorption. Moreover, they have a very good Hall and electron diffusion lengths. Even though they are nanocrystalline, they are very good diffusion lengths. And its solution process is still unique, as I was saying before, so you can use it with the conventional printing technology to fabricate your solar cell. Let me just show you some example, the importance of the band gap, and the band gap is tunable. So by varying the composition of the perovskite, you can change the band gap of the perovskite. For example, this is the methylammonium lead iodine bromine. By increasing the content of bromine, you increase the gap of your perovskite solar cell. And moreover, moving from bromine to chloride, this is methylammonium, lead, bromine, chlorine, you see that you can increase further the band gap of the material. At the very end, I mean, you see the methylammonium lead chlorine has a band gap of 2.9 electron volt, and this means that is quite transparent to the visible radiation. So it's a very transparent film, thin film. So this is very important because you can tune the optical property, and then you can use this material for a see-through application, as Morten Madsen was showing today. So this is a way to, for example, to handle the crystallinity of the solar cell. You put this material in methylamine, and then after you have a recrystallization of the solar cell, and you see here, which is very transparent. This is a methylammonium lead bromide, and then you see with a methylamine treatment, you can have a very good recrystallization of the perovskite and very good transparency of the solar cell. Here, the AVT, average visual transparency of the solar cell after the methylamine treatment is very large, is 56%. And then you can scale up this large band gap material, for example, to modules. These are modules of 10 or 6 centimeter for each side. And the efficiency, you see, is efficiency in this case is 5.2, 5.3, 5.3, and the transparency is increasing by increasing the contents of chloride. This is without chlorine, this is 4% of chlorine, and this 30% of chlorine, and the AVT is moving from 50 to almost 60%. So this is also a different way to use perovskite for see-through application. So we have a large project in Europe which is called City Solar, where we are developing these activities. And okay, I will show you. This is also the same plot efficiency as a function of transparency. And then you can see that now with perovskite, you can get the efficiency and transparency much better than disolar cell. Disolar cell are this green here. Now with perovskite, you can push efficiency and transparency much more to a higher value. So for see-through application, I mean, perovskite looks like to be better than disolar cell. Solution process. Now, let's see what we can do with material in solution. So what kind of technology we can use to fabricate our solar cell. So it's a very simple, sustainable, everyone in the world can do it. So this is a fabrication of solar cell. This is the kind of the stack. So we are depositing in the first step, we are depositing via slot die the nickel oxide on glass ITO. This is the nickel oxide, and then you do a thermal treatment to have crystallization of nickel oxide. This is the precursor of perovskite. You see it's very transparent, but you see when you have, and then we are depositing this on the glass. Then we need to get the crystallization, and we do crystallization with vacuum. You see vacuum treatment, and then you see the crystallization. Now the perovskite is quite black, and the final treatment is a thermal treatment. Then we print, we are slot die coating, also the C60 and BCP, so the other layers, still slot die coating and still vacuum treatment to get good film. And the final, this was a module, the final is the thermal evaporation of the contacts to create a working module. So as you have seen, all the layers are printed. It is also a larger module. So all the layers are printed, but the last layer, which is a metal electrode. So this is one of the open field in the research, how to develop printable electrodes. So you can use carbon, but besides carbon, can we use other printable materials for electrodes? So this is a very open question, and from technological point of view, there are a lot of activity to develop electrode that could be printed on as a last layer, because all the other layers can be indeed printed without any problem. Let me also show another way to create a perovskite solar cell. So this is very similar to the dye solar cell. So we have glass FTO, which is the transporting conductive electrode. Then we have a mesoscopic titania, all these nanoparticles, perovskite, sorry, and the old transporting material, which is a molecule, which is, for example, spirometal, and then on top, the electrode, which is gold. So this is the, let me see if I have, no, this is the, for example, a PEM image of this solar cell. You see the mesoscopic region here, and the overhead overlayer of compact perovskite, and then the whole transporting material, titania, compact titania, and FTO. As you can imagine, there are many interfaces in this solar cell, the interface between perovskite and titania, the mesoscopic titania, the compact titania, the interface between perovskite and the whole transporting material. So there are so many interfaces, so to the control of interfaces is very important. So this could be done, and this was what we have done also with Costa, Manos Kimakis, and many other in the graphene flagship activity. So we were proposing to use two-dimensional materials for tailoring the interface properties. Well, why two-dimensional material? Because two-dimensional material are many. So you have a very large library of two-dimensional material that can be used at the interface. You can use let's say, printing technology to deposit two-dimensional material. You can even use two-dimensional perovskite on the top of three-dimensional perovskite, because increasing the size of the cation, the organic cation in the perovskite, you can separate the layers, so you can create a two-dimensional perovskite, which is nowadays very used. And in this way, you can tune the interface and also the perovskite properties. And many people around the world are using two-dimensional material everywhere in the cell to improve the efficiency. And then you can see here the star here are those results, those research paper that were using two-dimensional perovskite. So two-dimensional perovskite is also a very important way to improve the efficiency as well the stability of the perovskite solar cell. Now you can imagine how complex could be to make a two-dimensional perovskite on the top of a three-dimensional perovskite. It's very simple. And then you see, let me show you here. So you see, you create the conventional perovskite solar cell like blade coating, as I was showing you, or slot die coating, as I was showing you before. You create the three-dimensional perovskite. Then on the top, you add a molecule, and this molecule, which are large cation, that penetrates on the surface layer of the 3D perovskite and creates the 3D perovskite. So you just print on the top this, you add this on the top this molecule, then you make a thermal treatment, and then you create on the top of 3D perovskite the 2D perovskite. So it's a very straightforward way to create an heterojunction between 3D and 2D perovskite. And you can do this not only with the perovskite, you can do also with graphene, molybdenum disulfide, and so on and so forth, other 2D materials. And you can show that this is indeed quite important for stability, for example, of the solar cell. Let me focus, however, on one particular 2D material, which is the MXenes. So MXenes, like titanium carbide material, are ceramic material, but they are layered two-dimensional shape materials. You see, I can show you here some of these material. These are flakes. You can see the 10 image. These are flakes of titanium carbide MXenes, and MXene could be semiconductor or metallic. Usually are metallic, but you can create also semiconductor like ceramic material, and they have a very peculiar properties that I would like to show you here in the next slide. So this is the work function of these mexins for different functionalization of the surface. You see here, this is just a flakes of mexins. The surface is very rich, so you can have different functionalization. You can have fluorine, oxygen, oxidilic group on the top and bottom surface of these flakes of ceramic material. So by changing the functionalization, for example, if you have only oxygen on the surface, then the work function is very high, like something like 6 electron volt. But on the other side, if you have an OH termination of the surface, the work function is very low, is 2. So this means that by varying the functionalization of the surface, by varying the termination groups of the surface, you can vary the work function from 2 to 6 electron volt, which for device engineering is a really wonder material, and that could be used indeed for improving the properties of perovskite solar cell. And indeed, I mean, we were using this property. I will not enter too much in the detail of the measurements that we have done, but let me show you. You see here that by putting mexins into the perovskite, we were able to change the work function of perovskite to get better band alignment, and then to improve the efficiency of perovskite from 16% to almost 20%. So by using mexins into the perovskite and in the other interface of the solar cell. So you see, 2D material is a simple, sustainable, printable way to tune the interface property in perovskite solar cell. This also improves the stability of the solar cell. Let me just focus on this one here. You can see here that the stability of the perovskite solar cell with and without mexins is very, very different. Okay, with mexin, you have a very, under light soaking, you have very good stability for more than 2000 hours. Without mexins, the efficiency drops very, very soon below 80%. So this is what I would like to show about a small area. Let me, in the last 10 minutes, I would like to show you how you can scale up to large area. Is it possible to scale to large area? You can do by using spin coating. It's a little bit critical, risky, because you have large area substrate flying around. If you don't keep it very, you don't stick very well on the spin coater, but you can use also large area machines, coating machines, to create your large area modules. This is a machine we have in our group. Is a large area slot die doctor blading coating, and then you see here we are just coating the tin oxide, which is an electron transporting layer. And then after the coating, you have a thermal air flux to remove the solvent, and also a thermal treatment, the yellow you see in the back, to dry the thin film. With this equipment, you can print the electron transporting layer, the perovskite layer, and also the hole transporting layer. So you can almost print all your photovoltaics. Of course, the last electrode is thermally evaporated. This is also another movie which doesn't work so well. But anyway, so at the very end, so you see here is a very large module produced with this slot die coating on more than 300 centimeters square area, and with a 16% efficiency. Now that you are able to create your module, so it's possible to assemble all these modules together to create a panel. And this is what we have done together, our friends in Crete. we have created more than 300, actually 360 sub-module, 11 by 11 centimeters square. The efficiency distribution of all this module was more or less, an average was 13, the maximum was more than 16%. And then we assemble all together to create panels. You see the panels, 90 by 60 centimeter, are obtained with 40 modules, 11 by 11. Of course, to put all these modules together, you need to laminate all these modules together and fabricate the final panel. I will show you a movie how to do it. So you put all these sub-modules together. Okay, first you need to select the best combination. You need to sort. Then this is the assembling. You need to connect electrically one module with the next one in a series parallel connection. This is the lamination material, which is in this case was AVA. And this is the electrodes. Then this is the edge sealing. And then this is the back sheet of the panel. And the front sheet, in the front was glass. This is the laminator. The laminator goes, closed everything, and then makes vacuum and then temperature. And then at the end, you create this panel. These are the initial tests. Then we assemble the solar farm in Crete, and this was almost 2020. And we start to measure all these solar panels for several months and years. And this is what happened. So we started in June 2020. And then you see the nominal power of the farm was keeping for very well up to March 2021, almost 1 year. And we were able to measure important value like parameters like current temperature, voltage temperature, solar farm, nominal power as a function of the temperature. So this dependence of the efficiency, voltage or current dependence on temperature are very important because are the parameter those who are design solar farms are looking for, because they need to calculate the efficiency and the generation of electricity. After March, however, we saw a quite step drop of efficiency of the solar farm. What's happened? So we saw that, there was a lot of delamination in the panels. So there was a lot of way where water, humidity was entering into the panel. So we saw that, the lamination is a problem. So we need, and we developed actually now, we have a new generation, we'll not show today, but we have a new generation with the new lamination material that try to avoid this kind of problem we had with this lamination. Last but not least, but I do not have too much time, probably, it's possible to use perovskite solar cell in conjunction with silicon solar cell in a tandem configuration. So usually you have silicon solar cell, and then you convert up to 26%. But what's happening if I put a semi-transparent perovskite solar cell that absorb the blue or visible part of the spectrum, and the silicon will absorb only the red infrared part. So in this way, with the tandem configuration, you reduce the thermalization of the charge. So you recover all the energy you lose for thermalization of the charge. So you can consider that you can get better efficiency, more than 30%. So this is what we have done. We have created a perovskite solar cell, a silicon solar cell, and then we have put one on the top of the other. And this is what we got. You see, this is the transparent top cell. This is the silicon solar cell that we cut to fit the perovskite solar cell. and then we put together. And you can see here, by introducing also 2D materials like Mexine, the 2D material, is possible to shift the efficiency from 24 to 28.7, and then by tuning a bit the perovskite solar cell is possible to reach 31% of efficiency. So this is what now the company are doing, the silicon company are doing, like Longi and so on, probably heavier. See, this is just the tandem as a function of time. This is efficiency as a function of time. And then you see that now the record belongs to a company, Longi, a Chinese company, that has a tandem efficiency almost 34%. So this will be the next wave of solar panel, very high efficient solar panel, which are obtained by coating the silicon solar cell with a perovskite solar cell in a tandem configuration. Let me close. This is a machine that allows to do this, but I mean, let me close with overview on the sustainable action one can do. So first of all, I was telling you that, I mean, we have lead inside, so we need to develop something which do not contains lead. And one of way to have a lead-free is to use tin. There is a lot of effort worldwide to improve the tin. So far, the efficiency of tin perovskite is around 14%, well below the one of lead. So I believe we need to do additional effort to push this efficiency more than 40%. Another point is to use green solvents. So there's a lot of solvents involved in the fabrication of perovskite solar cell. Many of them, like DMF, are not completely green, are very hazardous solvents. So we need to move in green solvent for the fabrication of the solar cell. This is a way to go. Another way to go is also to move part of the total fabrication of the solar cell, at least for industrial purpose, from the printing technology to the vacuum deposition. In the vacuum deposition, you do not have solvents involved, and then in this way, even though the equipment will cost much more, but in this case, you will not have the problem of use of critical solvent, recycle the critical solvent, handling of the critical solvent. Of course, I mean, as I said, these are much more expensive equipment compared to the printing technology. So printing is very good also because the equipment and the capex is very, very low. That's it. I mean, I think I could finish now. I have a lot of other slides, but I mean, the time is over, and I probably say what I would like to say. Thanks a lot.
Thank you very much, Professor Di Carlo, for this very educative and very impressive presentation. Let me check the chat for questions we have already. So Manas is asking, okay, first, he says, thank you for this insightful presentation. So I think he refers to the metal diffusion, like silver or gold, and stability issues in perovskite solar cells, especially at elevated temperatures. So he's interested in hearing your perspective on this, especially considering the carbon-based metals, carbon-based electrodes, that is expected to overcome this kind of stability issues due to metal diffusion, I guess.
Yeah, metal diffusion is a problem everywhere in electronics, okay? Also, silicon technology has a problem of metal diffusion. So there are ways to use interface engineering, like in the silicon technology, I want to say, to reduce the metal diffusions. And this is the way to use also 2D material we have seen could be useful for reduce metal diffusions. So this is the way I would like to say this is a solution. For example, you can use or let's say ALD or sputtered alumina or sorry, not alumina, sputtered ITO or alumina, ALD alumina, just to make a protecting layer to avoid the diffusion of the metal. Or you can use a metal alloy to reduce the diffusion. Of course, carbon is a solution, okay? Carbon is a good solution for having a good electrode. The efficiency is still a little bit below the conventional one, but also stability-wise, I mean, it's very, very stable. So I believe also the carbon is a good solution. For indoor, for sure, when you don't need really modules. For modules, I would like to say it is a little bit more critical. So maybe for modules could be a little problem, but I mean, it's a way to go. Of course, I mean, you cannot use for tandem because you need semi-transparent electrode. So for tandem, which could be one of the first application of perovskite, carbon is not an option.
Okay, thank you very much. Mr. Fonseca is asking about he's wondering if you have tested printed solar cells on flexible substrates. If yes, what materials did you use?
Okay, yes, we have tested on flexible substrate. Sometimes you cannot transfer directly what you develop or optimize for rigid substrate on the flexible substrate. Typically, you can use the same stack. For example, you can use nanoparticle of nickel oxide, then the perovskite, and then a C60 or PCBM and BCP. So this is the one of the typical stack. Recently, we are in a project where we need to develop the NIP configuration. So we will do PET ITO, then tin oxide, perovskite, like formamidinium lead iodide perovskite, and then PTAA, and the last, the metal that could be carbon or a metal like equivalent to the gold, even though the gold is not an option because, I mean, it diffuses, and then also the cost of gold is not sustainable.
Okay, thank you. Another question here is about what is the best perovskite structure or composition you have tested, and which one is giving the biggest, the highest efficiency?
Okay, in principle, the highest efficiency could be given by the FAPI, even though the FAPI is a bit critical because you have both two delta and alpha phase, and then you can move easily from one which is photoactive, the alpha phase, to the one which is not photoactive. So it's a little bit tricky, and it's not simple to get the top efficiency with that. So what we are using is usually cesium formamidinium lead iodide with a little concentration of bromide. But this is what mainly we do. For example, 10% of cesium, 90% of formamidinium, which is a quite good, where we get more than 22% efficiency for the perovskite.
Okay, thank you. A similar question about semi-transparent cells on flexible substrates. So, what is the best device structure for semi-transparent? I guess they refer to the top electrode.
Yeah, I mean, one of the critical point is the top electrode, how to deposit the top electrode on the perovskite solar cell. Let's say, if you want to do in a simple way, it's better the NIP configuration, because in the NIP you can deposit let's say electron transporting layer like tin oxide, then perovskite, then PTA, and then you can sputter at very low power directly on PTA, or you can print a buffer layer like vanadium, or printing or thermally evaporate a protective layer like vanadium pentoxide to protect from the sputtering. In the case of PIN, I mean, it's more critical because the layer like C60 or PCBM is very sensible to the spattering. So you need to do always a very protective, a protection layer. Or you do ALD, then you do ALD, like tin oxide ALD, or zinc oxide probably, or you can put the nanoparticle of zinc oxide, like azo or other zinc oxide. So we will submit a paper on this because we have done a very thorough investigation of what kind of nanoparticle you need to put on the top to avoid the damage of the spattering of ITO.
Okay, thank you. Another question this time about 2D materials and machines. If you have tested the solar cells only using 2D materials as an active layer, and specifically machines, and if yes, what is the performance of the devices?
No, we have not done. For absorber is very critical because you need some thickness. You need at least 400 or 300 nanometer. Maybe a bit less in the case of molecule, but I mean, I believe for this kind of material, even with direct band gap, you need 300, like in the case of perovskite. So at the very end, compare the 2D thickness, 300 nanometer is a thick layer. So maybe it's not too much convenient. But I want to say that it's possible to do fully 2D. People has used 2D perovskite, fully 2D perovskite as absorber. And then indeed they got a very, very good results, especially when instead of putting the layer one on the top of the other, they tilt the absorber in the vertical direction. So the plane are in the vertical direction. In this way, they got the most efficient solar cells. So it's doable. I've not done so far, but it's doable, especially with 2D perovskite, yes.
Thank you. And I think one last question, because we don't have time. You can contact directly Professor Di Carlo if you want further discussion. So, what is the best way to do encapsulation for flexible solar cells?
Yeah, I believe you can use one of the resins. I mean, I believe you can use polyurethane, for example. Polyurethane works well, and I believe there is a paper from our group on polyurethane, and also we are developing a new encapsulation strategy, and the paper I believe will be polyamide, so will be out very soon. So there are these materials, polyurethane, polyamide, so that could be indeed used for encapsulation, also flexible structure, flexible and rigid structure, yes. And fast, I mean, then of course, I mean, maybe you need a barrier, a more rugged barrier. So I believe also LD on the top, LD overlay like alumina, LD could be good. But so far I didn't make this kind of test.
Okay, thank you very much. So I would like to thank you very much, Aldo, for your acceptance to participate in the school. So you were the last speaker of the school.
The long school, okay. It
So
was really a pleasure, Kostas. And I say hello to everyone. Okay, bye-bye.
Thank you very much. Bye-bye. So just now to finish the school. So with this session, we close the school. I would like to thank you very much, Irini and myself, for your participation. Now we're collecting all the information from the speakers. I mean, the PowerPoints, the recording, the video, and we will upload them. Now we're opening a Moodle platform, and we will upload all the material there. Sometime next week, we will share with you how you can log in to the Moodle platform, and then you can find all the material to study further. And we plan around 10 days. We will send in advance an email to launch the Moodle test. So everybody, we will have 3 hours, let's say. You can go there and run the test, and then we will have the results. So the plan is to have the on-site training for the top 25 students We held the on-site training in Portugal, in Lisbon, the last week of June. So we will keep you posted through email. We hope you enjoy the school. Thank you once more for your participation. Bye, everybody.